Welcome to the Helipot Corporation. This is the familiar Plant 1 area at 916 Meridian Avenue, our headquarters building. And this is the 1001 El Centro Research and Development Division headquarters. This morning, a meeting has been called in the office of the Technical Director to go over the R&D work program.
Good morning.
Oh, good morning, Bill.
Jim's coming. Here he is now.
Good morning, Jim.
Hi, hello, Bill.
All right.
Have a seat, fellas.
Auto looks sharp this morning, doesn't it?
Well, thank you. I have called this meeting of department heads to review the R&D division's general objectives and to have you, Bill Denniston, and you, Jim Gordon, go over our general work programs. Let's first take a look at our chart of workflow and see how this fits into our general program. Work for the R&D division originates in the New Products Committee from customers, from our representatives, and from other departments. Ideas requiring evaluation and research go into the research department. Ideas requiring basic new designs go into the development group. The customers' special orders go directly into production engineering. The work flow passes from the research division through the development department and thence into production engineering, through production and out to the customer. In order to follow this workflow pattern, we have set up the R&D division according to this organization chart. The Research and Development Division is divided into two groups, the New Jersey and the South Pasadena groups. The two groups are identical, however, there are more men in the Western group. The diversification in the subgroups is caused by this difference in personnel. The Western group has a basic research directed by Bill Dennison, consisting of laboratory services, applied physics and servos, equipment design, ceramics, and product and applications research groups. There is also a group headed by Jim Gordon, who is our Chief Development Engineer. Their prime responsibility is the development of new projects through the efforts of the project design engineers. They have, as well, service groups of drafting and model makers. The Eastern plant has the same functions, but they are much simpler. Service function, lab and drafting, equipment design, product and applications research, design and development engineering. Let's look at our South Pasadena section of this chart. Bill?
The research section is charged with the responsibility for invention and research leading to new products through lowering production costs and better yields by design and material changes in the product and development of automatic production equipment. These objectives are accomplished through 5 groups. The first of these is the lab, under the supervision of Keith Schultz. The backbone of any R&D department is a good testing laboratory. Keith, will you show us around your lab, please?
Certainly, Bill. We have extensive environmental testing facilities. Here, Virg Abrams is measuring the torque of a potentiometer in our large chamber. The pot is mounted on a specially designed door so that it is completely within the environment, yet accessible for rotation from the outside. This chamber simulates conditions of temperature, humidity, and altitude. Recent developments in high-speed aircraft and missiles have necessitated components which function during extreme conditions of vibration. To aid in developing such products, the lab uses this 100-pound shaker system. Here, Bob Cole and Bill Kitchens are monitoring the contacts of a pot while the pot is undergoing low-frequency vibration. Bob McDonald is using the shock tester, which was built to Jan S44 spec. On it, our pots are subjected to shocks in which the acceleration is up to 100 times that of gravity. This test gives us information on the mechanical strength of the pots. This rotary accelerator, or centrifuge, is being used by Charlie Braun to apply a uniform acceleration to one of our pots, such as it would receive in the launching of a missile. this machine is up to 100 times the acceleration of gravity. In addition to the environmental testing done by the lab, general testing is done as a service to the other R&D groups, as well as to other departments in the company. Here, Mills Miller and Chell Livnasseth are starting a rotational life test on a change in coil contact design for one of the production engineers. Al Jenny is performing a linearity measurement on one of our potentiometers. This linearity tester was designed and built by the lab section. Because of the large amount of costly and complicated equipment, an instrument repairman is needed. Leo Hansen does this job for us.
The second group in my section is the Applied Physics and Electronics group, supervised by Stan Schneider. Stan, would you show us some of the things you're doing, please?
I'll be glad to. Let's start with a look at Jim Gordon's Veriductor, one of the new products we're preparing for production engineering. The Veriductor is a component whose inductance is varied by rotation. Clarence Golden is the project engineer on this job. The Veriductor consists of a movable magnet, a toroidal coil, and a fixed magnet. It is a very simple passive circuit element covering an inductance range as great as 100 to 1 with high Q and no contacts or wearing parts. Hugh Parrish is now using the toroidal winding machine to wind a coil with an inductance ratio of 150 to 1 for a B-size Veriductor. The biggest problem confronting the nonlinear group is producing coils with good conformities. A major facet of this problem is the accurate electrical transformation of information from the cam table to the winding carriage. Recent improvements in this transformation have been affected by the installation of a new 400-cycle servo system built by Bob Levin and Fred Hiraoka. Here we see the cam table in operation, remotely controlling the winding lathe. Here is a shot of the action of the wire winding guide as the cam table calls for maximum correction. Note particularly the high speed of response with no overshoot. In spite of the improvements that have been made, the system just shown still is not capable of winding coils of the highest accuracy, since it is in essence an open-loop system. To correct this fault, a new, greatly improved closed-loop winding machine has been designed and is being built. Here we see a block diagram of the new system. The heart of this system is the digitally controlled function generator. Ebish Nuban is shown operating a breadboard model of the master function generator. He is changing the output from 20 to 60 volts. From the customer data, the information is taken and fed into a computer, which results in a tape which controls the digitally controlled function generator. From this, by means of the servo control, the lathe is controlled and results in a resistance function which is the same as originally specified by the customer data. This system is expected to result in a tenfold increase in the accuracy of our pots. In addition to our wire-wound pot program, we have devoted considerable effort to a high-temperature film pot. Svein Rasmussen has the responsibility for adapting these film pot elements to potentiometer use. How are the ceramic pot life tests coming, Svein?
Very good, Stan. Here is an example of one film pot element that has been through over 1 million revolutions, and the noise has dropped to below 50% of the original value. And as you can see, there is still no noticeable wear on the element. Another and somewhat different aspect of our work is obtaining a good linearity in our film resistance elements. By means of servo control, the element is made to conform to the desired function and linearity. Here you see the actual tailoring being done. By this method, we're able to reduce the linearity error to as low as 0.2%.
Here we have a typical example of a tailored film resistance element with its linearity traced before tailoring and afterwards. We have an improvement of about 20 times.
That's fine, Spain. How's the design of the production tailoring equipment coming?
We're doing fine. The service section is well along.
This is our new high vacuum equipment, which just came in yesterday. Ed Nakaji will have the system running in a few weeks.
The third group is equipment development, supervised by Frank Pritchley. Frank, would you tell us about some of the things you've been working on, please?
I'd be glad to. First, let's talk about the wire linearity tester. This is the breadboard model, and this is the production unit recently completed by Ken Miller. Ken, would you mind explaining how this equipment functions?
The purpose of this machine is to select very linear wire for our precision potentiometers. We are training a man from the production coil room to run this tester. Briefly, the wire passes over this system of pulleys where a function of its error is measured. The error is then computed and plotted automatically on this recorder. From this chart, we can determine the linearity of the wire. The front panel hides the complex computing and traverse mechanisms which we see here. The major components are the mechanical integrator, servo motor, servo amplifier, gearbox, and drive motor. All of this combines to give us an extremely useful machine which will test wires as small as 9/10 mil at speeds up to 400 feet per minute and will measure linearity errors as small as 1,000th of 1%. This will enable us to produce more accurate potentiometers.
Selected high linearity wire from the wire linearity tester is capable of being wound into very accurate coils. We then find it necessary to improve the winding characteristics of our winding machine. Tony Sardahelli, would you please explain some of the recent improvements in the continuous winding machine?
We have improved the main drive in accuracy and in strength so as to give a very smooth feed to the mandrel as it passes through the winding head. The smoothing out of the mandrel feed enables us to obtain very high accurate windings. Recent winding head redesign enables us to accurately control the resistance wire tension while the machine is operating at full speed. Servo control of the mandrel tension further improves the accuracy of the finished coil. A new push-type helixer has been developed to eliminate coil damage caused by old-style helixing.
Well, how are the composite tests of the completed machine turning out, Tony?
Everything looks fine, Frank. We should start production design cleanup in about 2 weeks.
Potentiometer shorting segments is a problem that has been receiving a lot of attention by Harold Goody and Ralph Kern. This equipment sprays molten metal on the prepared coil surface. The idea was developed in the New Jersey plant. Use of special mass makes this a high-speed production process. Environmental tests of pots with metal sprayed short of several materials are being made now. We expect to have this equipment and process ready for production within a month.
In addition to equipment design, this group is doing much important work on mandrel design and mandrel installations. Here, Al Green is shown winding a metal card for evaluation. The fourth group is the ceramics unit under the supervision of Tom Place. Since this operation will be new to most of you, we will take a quick tour through the whole thing from raw material to finished parts. Tom, will you be our guide, please?
Thank you, Bill. I'll be very glad to. Ceramic materials are produced from the action of extremely high temperatures on mixtures of natural minerals. A ceramic product of one kind or another is the only satisfactory material for use as an electrical insulator at high temperatures. Steatite is the most common ceramic insulator in use in the fabrication of electronic equipment, largely due to its ease of fabrication and to its high dielectric values. Steatites are made up of 80 to 90% metallic 5 to 10% of clay, and small percentages of magnesium carbonate, barium carbonate, and other small additives. An accurately weighed batch of these materials is put into a so-called Molar Mixer. Don is adding a definite amount of water and a small percentage of organic binders. The action of this mixer produces an intimate mixture of all the materials in a semi-plastic consistency. This is our base body, which is processed in a number of different ways. The semi-plastic volley from the Molar Mixer is placed in the chamber of an extruding press, evacuated, and then extruded through a die at high hydraulic pressures. Tim is now operating this press. Tubes, rods, and various shapes of this nature are made by this method. These extruded pieces are placed on pallets and completely dried out. When these extruded pieces are completely dry, they have exceptionally good strength. And in this condition, it can be easily cut, drilled, or machined to the desired configurations. For certain intricate and irregular shapes, the wet material from the Molar Mixer is dried out and crushed down to fine granules. These dry granules are charged into a pressing die, such as this, and formed to shape with very high pressures. These so-called dry-pressed pieces may be machined or drilled to a limited degree. After the various pieces are machined and finished and thoroughly dried, they are fired in a typical high-temperature ceramic kiln. Steatites are fired to about 2350 degrees Fahrenheit and held at this temperature for 4 hours to obtain complete heat reactions. After these pieces have been fired, they are very hard and are impervious to moisture. Various pieces are cleaned and perhaps polished and are then ready for use as ceramic dielectric material. Various coatings may be applied to the surface of these ceramic materials. In this case, we have applied a film of resistance material. The resistance material is mixed with a glass, and the glass is fired on a ceramic base, which produces a smooth glass firmly bonded to the base material. Silver electrodes are then applied over the base for solder connections. This ceramic silver is fired on and forms a solid attachment to the film and to the base material. These elements are now ready for installation in potentiometers and similar electronic equipment.
The last and a very important group in my section is the product research group supervised by Jack Howdyshell. Jack, would you show us some of the things you've been doing recently, please?
Yes, Bill. My group is continuously investigating new materials which will improve the quality of our pot. Pete Heller is evaluating several molding compounds.
This machine here determines the suitability of the various plastic materials by expanding a rubber mandrel inside the sample housings. This new dial phthalate appears to be a much superior plastic.
Our new single-turn pots will use this material. Now let's go see Bill Tholey, who is responsible for increasing the temperature limits of our pots, and have Bill review the 125 degree centigrade program.
First, we studied prints of all Helipot models and tabulated each material according to its application. In this manner, we were able to establish the maximum operating temperature limits. Let's take a look at the changes required in a typical model. For plastic materials, a heat stabilization was required. The springs had to be heat treated to prevent relaxation of contact forces. Stainless steel ball bearings were required in the absence of heat-stable lubricants. And finally, more oxidation-resistant nichrome and precious metal alloys were required. The necessary materials and process changes were made, and prototypes were built for test.
Here is Bob Jenks making a linearity run at 125 degrees centigrade. This portable oven was constructed so that the pot could be mounted on the tester and checked while at the elevated temperature. Similar setups were used for checking all electrical and mechanical characteristics, both initially and after prolonged heat exposure. We are currently working to extend the maximum temperature still higher. Our goal is 250 degrees C and up. Here, Bob Freeman is removing some aluminum parts from the oven. These are being tested for suitability in Helipot high-temperature construction.
As part of our program to solve potentiometer noise, Norm Sneed has developed a special microscope technique to cause semi-transparent noise particles to become visible. Norm is shown here using the dark field technique. Dirty pots are cleaned in an ultrasonic cleaner with suitable solvent or detergent solution, as you see Ivan Atkins doing here.
Here is a typical pot before ultrasonic cleaning. With the removal of the particles, the pot wiper can now make positive contact with the coil so that low noise results and slider opens are eliminated. Here are before and after views shown simultaneously so that you can better note the improvement. Some wire drawing films and other particles are on the resistance wire as received from the wire manufacturer. Some of these films adhere to the resistance wire too tightly to allow removal by ultrasonic cleaning.
These particles and films are removed by a process being developed by Norm Sneed. Norm, would you describe this, please?
Yes, Jack. This process includes the degreasing of the wire, rinse, electropolishing, plated, and re-rinse and re-spooled.
Beautifully cleaned and plated resistance wire is thus produced.
Here to summarize our noise program is Will McCann.
The cleaning of resistance wires and coils is not the complete answer to a low-noise potentiometer. Our research has indicated that further processes and operations are necessary. One of these operations is the coating of a plastic housing such as this with a polyvinyl enamel. Our future aims are for the procurement of a better plastic which will meet all potentiometer requirements, plus having the additional strength material such as this. Finally, the pot must be assembled in an enclosed, dust-free work area. Thus, with resistance wire plating, ultrasonic cleaning, the coating of plastic housings, and assembly in a dust-free work area, the ultimate in noise-free potentiometers may be achieved.
Much of the product research group's effort is spent assisting production on difficult problems. Jack Hoddishell is seen on the AN line with foreman Murray McIver. And now they are at the recording linearity tester.
Thank you, Bill, for the comprehensive review. And now, Jim, let's hear about your department.
Well, it's not only design responsibility that keeps us busy in development engineering group, but the rare privilege of being able to take the products of research and weld these things into tangible new products that our factory can build. If we follow two of Helipot's ace designers inside development engineering, we can get a good idea of what they do. Helipot Development Engineering is charged with the responsibility of taking the products of research, combining them with sales requirements, and making the necessary design compromises to assure a good product for the factory. A great deal of imagination and ingenuity is required of our development designers in this process. Helipot owes its actual existence today to the development and delivery of a completely new product to industry. Al, would you show us something of what you're doing there?
Yes, we have just completed this precision dial. It reached to 1/10% accurate.
That's a very fine looking job. Thank you very much, Al. Hello, Herbert. Are you designing something too secret, or can you tell us about it?
Well, it is all right if you look. We are just finishing the development of our new 1/160-inch part. We are feeling very good about this.
Oh, that looks like a little jewel. That's a very nice job, Herbert. I hope you do many more like it.
It is always nice to build good things.
Thank you, Herbert.
Goodbye.
Hello, Potentiometer. I see you just finished tests on the new 6-inch precision potentiometer.
Yes, it looks pretty good.
This is one of the finest precision potentiometers that has ever been designed by Helipot or anyone. Did you find, Nob, that when you were designing this potentiometer that the use of new materials helped?
Yes, it really helped in the design.
Thank you very much. It sure looks like a fine job.
Thank you.
Thank you, Jim. This concludes our meeting, fellows.
Coffee break, Bill.
Good idea. I believe it's my turn to buy, Jim.
I hope that this has given you a better understanding of the role of the Research and Development Department in the Helipot organization. This is the manner in which we maintain Helipot as tops in their field.